Okay, they are. All right. Yeah, sorry about that. One of the captains, when they were making it, didn't embed the videos, meaning every time you click the link, it had to bring you to an entirely different tab, which is super annoying when you're recording. So we're embedding everything, and it should all work now.
Should we pick up where we left off or just start all over again?
Probably start all over because we need to re-record it.
Okay, okay. Next
Also,
slide.
we messed up the beginning.
Yeah. Next slide. So these are just these are just an overview of okay, different design ideas for the robot. Basically what makes what different parts of a robot to go. Each of them have their own pros and cons and can be and are some are specific for different situations. Others are just general purpose. Next. So the core chassis for how a robot moves is there's three different types. This is one of them, and it is the tank drivetrain. It's fairly simple. It's just a bunch of wheels all interconnected, and yeah. The pros is that it's fairly simple. It doesn't require that many complex parts, and is pretty simple. Some cons is that it doesn't have a shifter, which means that you can't go fast and then suddenly go slow in an instant. Um, and yeah, it's pretty basic. Next slide. Now, the West Coast drivetrain is the one that the supplier that they give us. It's essentially the base model.
That's the tank drivetrain.
Tank. I thought that was. Oh well.
This is the super expensive one that we bought.
Yeah. Some pros is that it has a shifter, which I explained just now. All the moving parts are inwards, meaning there's a lot less. There's like less chance of stuff getting in between them and possibly breaking the entire thing. Some cons is that it's pretty expensive, and yeah, pretty much it. Play the video.
That's all you had to show. I was just trying to show the how the drivetrain works. Like you can see, you have to move each side independently. You can't really do like fluid motions. That's all I was trying to show with that
Yeah,
video.
in order for it to turn, what the robot does is it speeds up one side and slows down the other, or just speeds up one side and doesn't move the other. That way it can turn.
Yep.
Um, the West Coast drivetrain, as you can see here, is a. This is the super expensive one that we bought. It has a shifter. It essentially goes from the normal speed to around 8 feet per second, I think, or 7 feet per second. And if it turns on all three motors on either side, it can go all the way up to 20 feet per second or something
Yeah,
insane.
I think the intervals are 8 feet, then to 17, that's 20.
Yeah. It's basically the purpose of this is it's able to shift from a normal speed. So, because you don't want to be zooming around at really high speeds constantly. But when you're, let's say, trying to go around another robot or trying to maneuver around a defending robot, the extra speed boost means a lot. So, yeah. Next. Right. So, this is a swerve drivetrain. It is a very difficult drivetrain to build. It's essentially, if you think of it, think of a shopping cart wheel and how it's multi-directional and it can spin. Essentially, we're doing the same thing here, where you have two motors per wheel, or sometimes more. Usually, one motor controls the rotation, and one motor controls the actual wheels turning. This allows the robot to move in literally any direction at any time and like parallel park into like very tight corners or whatever, maneuver around things really smoothly and really quickly. You can see it in that video over there.
Yeah, so those are the pros of it, and the cons would obviously be that the
Hard.
maintenance would be very hard to like keep it up to its peak condition because you'd have to maintain each of these separate sets
Yeah.
of motors, whereas in the West Coast you only have 2 sets of motors, but here you have 4. So just because 3 out of 4 are working doesn't mean the entire robot's gonna work. You still have to make sure that other set of motor work, and if that set of motor doesn't work, then your entire robot is basically garbage and it can't move.
Yeah, also,
So that's the main con.
you can't really buy a swerve drivetrain.
Yeah, and it's not
You have to
viable. You
custom
have
build.
to yeah, which is why we need a CNC because as you can see, all those parts are literally like perfect fits for each other, and it's kind of hard to hand make.
Yep. Can you play the video? Oh yeah. This is Yeah, you can just see how it's literally just spinning, going forward and backwards. You can basically spin in place as well. So if you need to rotate or aim, you can do that. Yeah, it's pretty good for like the just like the West Coast drivetrain, you can maneuver around things extremely easily. This one even better because not only can you maneuver around almost anything, you can also aim from you can aim things without actually having to make some sort of rotation platform. Next. Right. Oh, okay. So wheels, right? Wheels are actually really important because this is what's going to be actually in contact with the majority of the parts on the field. Depending on what type of wheel you're using, can greatly affect how you perform, what task you're doing. So this is the high grip wheel. This is the standard wheel that comes with nearly every single tank drivetrain. It is standard. You can see it's pretty high grip with those external layers there. Also, the only problem with this is that it tends to wear down. Um, when it does that, it starts to like slide, and also a lot of grime and random shit gets stuck in between the different parts of the wheel. Pros and wise, yeah, this it's very simple. It is the most common wheel. You use it most of the time for drivetrains. It's literally interchangeable with most wheels except for the squishy ones. It's stiff. It's hard enough to withstand a lot of things. So yeah, cons. It doesn't really have any function besides acting like a normal wheel should. Right. Okay, compliant wheels. So these are the squishy wheels. You can look at them. They're like different types of rubber. The different colors symbolize the different strengths of the squishiness. Guess that's a term. But the green ones are the most squishy. Red, blue, and then black. These are primarily used for picking up different parts off the field. For example, most of the launchers are actually made out of this. The intakes, the outtakes, the majority of those actually use this because the squishy ones are the ones that allowed you to actually pull things in without breaking anything, without getting stuck and all that, because it allows room for mistakes. You know, because if a field element is a square, right? Depending on how you pick it up, it might be wider or less wide because diagonally the square is longer than the square on the side. Meaning that if you pick something up diagonally and then the wheels are too stiff, that means it's going to get stuck. But if you take it on the flat side, it wouldn't get stuck. So that's why compliant wheels are pretty important. Cons, they're squishy. They cannot be used to actually like support any weight because they're way too small, too squishy to do that. They also can get damaged. Next, right, smooth grip. So these are the primary ones that we use for our drivetrain because the smooth grips are both very stiff, but also because it lacks the different um, what's it called bumps like the high grip does. It allows you to more easily get through things, get cleaned. Also, it doesn't get stuck on things. And usually, when it starts to wear down, it's continuing to function similarly. It doesn't lose its grip as much as the high grip does. Pro cons initially when you have it fresh out of the box, it is not as high grip as high grip, but This allows you to move really fast forward or in a linear direction. Also allows you to turn because when you're doing a let's say a swerve drivetrain, a high grip wheel will be more difficult to turn because of the high friction. Yeah, next. Mechanism wheels. Okay, so these are we're getting into the whoa and interesting wheels. This is a mechanism wheel. As you can see, it's a wheel with many smaller wheels facing diagonally. You can see that there's these rollers that are connected to the edge of them, and each of them are facing in different directions. One is a left mechanism, and the other one is a right mechanism, depending on which direction they face. The mechanism wheels are so nice because they allow you to point whatever thing that you're using towards a certain direction, right? If you rotate it, if you rotate a right wheel constantly, it will start dragging things. I think if you rotate counterclockwise, it starts to drag it to the right. That's what I'm seeing from that image. And essentially, this allows you to maneuver your robot also in a certain left or right motion without being swerved, but also allow you to maneuver certain like parts and stuff like fuels cells, those like yellow balls and stuff towards the intake. You can see that later on. Cons, they're so expensive, bruh. It's like $30. It's whoa. It's very expensive and they're heavy and very easily breakable. Otherwise they're pretty cool. Next. The Omni wheels are like the other version of this, right? While the other one was diagonal, these are exactly 90 degrees or perpendicular to the wheel's rotation. This allows you to rotate to the left and the right directly. Primarily, this is used for you to move something to the left and right rather than moving it sideways or towards a certain direction. This can be used to. Usually, this is actually used on our robot at the what's it called, the chassis, because this allows us to maneuver the front much more easily than the back. Because when you're rotating something, like think of a car, right? There's a reason why your front wheels are the ones that turn left and right. Essentially, we do that with our front wheels as well. That way, it allows us more easily to turn. Cons, it's also hella expensive. Breaks easily, heavy. Yeah. Next. Right. So these are the climbing mechanisms. There's buddy climbing and solo climbing. Every single year there's some sort of climbing. It's what whether it's getting on top of something or pulling yourself up onto something. This happens nearly every single year. There's two types. There's buddy climbing and solo climbing. The majority of robots don't climb. Some do solo climb, some buddy climb. The more people that climb, the more points you get. In fact, climbing is the most points in every single game. I think it was 30 points last year. And essentially, you can see in here, solo climbing is just climbing by yourself. Buddy climbing is climbing with someone else or pulling a buddy along with you. If you can look at that video. So this is a buddy climb. So a different team is going to be pulled up by another team. See, pretty sick. Yeah, that way that both teams get onto the top one and they both get the points because you have an alliance. Yeah. Next. Okay, so there are different types of outtakes. Outtakes usually involve moving some sort of thing on the field into another area or shooting it into something, right? That's why this is the point here is the shooter versus dumper. The shooter you can see on the top right is something that fires it. It can aim, and based on where it aims, it can fire into different levels of holes, how high it is, etc., and all that can be changed. Also, one thing that we were talking about when we were doing this was actually spin. Because you're able to spin the ball midair. You can allow the ball to both curve and also for when it hits a surface, it will go in a certain direction, right? There's something called backspin and I think force spin. And essentially, let's say if you rotate the bottom wheels faster than the ones at the top, you start having the ball rotate counterclockwise downward. And when it does that, if it hits a surface, it shoots down very quickly. Last year, a major issue that some last or 2 years ago was that if you hit the back panel inside of the hole, your ball actually bounces out. So, putting backspin on it allows it to hit the wall and immediately shoot down and get it in without having it bounce out. Um, yeah, you can see. Yeah, there's the dumper. It's just you literally just dump all the balls into a single hole. You can see in that video, right? Yeah. The purpose of these is they can take in a lot of the balls and fire them all at once. Instead of shooting one ball at a time, it does everything all at once. Yeah. This is a shooting mechanism.
Alright, kick back, relax, and grab yourself a beverage. A hop if you wanna just bounce to my leverage. The evidence, as they say, is in the pudding. So show me the money like my name was Cuban pudding. It ain't fool's gold, it's gold, fool. Can't stop, won't stop, keeping it old school. So cool. Big spoon is my nom de plume. I keep it popping like a needle in a new balloon.
Yeah, you can
and if
see
you
some
don't
of them
know by
actually
now, then
bounced
you
out.
need more
Yeah, also, if you look at the outtake there, it actually has a hood that can go up and down. And based on whether or not it's facing upwards or downwards, you can change the height of which the balls get shot. All right, that's a climbing mechanism. Yeah, that's just a lifting climb. But yeah. All right, next. Yep. So the intake in every single match, we need to take in something. One last year was these types of balls, but each year they change. As you can see here, there are four different examples you can see there. There's the large spinning cylinder one. It's pretty effective. It just pulls in whatever directly inward. Depending on where it comes in initially, it's all going to be pulled up and bunched in. Uh, the one on the right, I don't know if you can see, is also a smaller version of this with multiple wheels rather than one long cylinder. It pulls it into a conveyor belt to be brought to the firing. The bottom right is another example of that same thing. It's just a closer shot. You have the different tubes and you have the wheels that spin at the bottom to suck it in. Um, and you can see right there that there is a horizontal version of it. Whoa, those don't exist too often. Usually we use those for trying to pick up something like a square or something that you're moving up and down. Our first year, we actually did something very similar to that. Uh, so yeah. Yep. So this is an example of an intake with a mechanism wheel. So you can see exactly how they work. So yeah, you see those mechanism wheels? They're facing two different directions, and essentially, no matter where you pull it in from, it will always be pulled towards the center.
Our intake's right on the edge of our frame perimeter, but we did manage to get a climber right here.
Yeah, because they're facing
Little
inward, they
sides.
will rotate each wheel inward towards the center. That way, even if the ball was shot to the right side, it will always get pulled into the center because of that wheel. Yeah, next. Okay, so lifting, right? So in each competition, you do need to lift something to somewhere, right? Because there's always some sort of height thing that we need to reach. So there are four types of things, right? There's one is the conveyor belt in the bottom. You can see that the ball is being brought up from the bottom to the top towards the firing mechanism by that long conveyor. On the right side, we have something called a double lift. It's basically two layers of a lift mechanism. The lift mechanism is usually the most simplest, but a double lift allows you to not only lift once but lift twice, so you can do triple the normal height. Um, that way, you have the base, the long thing, you have the second long thing, and then you have the third, whatever. Um, but yeah, it's actually a triple lift, but yeah. 254, the one they have here isn't that obvious, but they actually have it on the inside instead of on the front to do the double lift. But yeah, on the top left, there is a telescoping arm. Essentially, it is a single, very thin, multi-layered arm that telescopes out layer by layer, usually by pulleys. This is really nice because you can fit everything into a very small amount of space. Um, yeah, right. So in order to design things, we need to CAD it first. CAD is computer aided design. Essentially, you're using a 3D modeling type of thing, software, in order for you to design your robot, different mechanisms. It's super important because it allows us to create the robot without actually creating the robot physically. Because you can put in the same dimensions and everything and see how everything scales up. You can plan and make the mistakes while building it in the software. In addition, this year is going to be super important because by counting everything, you don't need to be designing on the fly. You can plan ahead for everything. And also, since we have a new CNC machine, this will allow us to machine out different pieces. Like you can see on the right, there's different holes cut into that metal. Nobody can physically do that usually. Usually, a machine does it using a laser cutter or plasma cutter that we're going to try and buy. Max, do you have an example of like a CAD model? All right. Is there any background noise for me?
No,
I
you're
think
good.
my neighbors are mowing the lawn. All right, Max is opening up the CAD right now. Yeah, all the computers in the engineering metal shop has Inventor installed already. Those are a few examples of the types of CAD that are available: Onshape, Inventor, SolidWorks. SolidWorks is Fusion 360, right? Um, Essentially, Inventor and Fusion 360 are the best options for doing CAD usually. These are professional grade. They cost literally thousands and thousands of dollars for you to just have per year. It's insane. But we have like a student license, so they give it to you for free. Um, but it's super taxing on your computer. It's gonna lag like everything. Onshape is a different version of this. That's a browser-based one. It allows you to basically do CAD and make edits while other people are on the same exact design, so multiple people can collaborate at the same time. Also, that design over there is pretty interesting. Oof.
No, he died.
I Let's go. He found a CAD. I think this is the Everybot CAD. But yeah, this is using Inventor. Yeah, you can see right there. he has the CAD model. Can you try and rotate it? Yeah, you can see. Yeah, you can move things, put things together. Um, yeah, a lot of almost every mechanical engineering boy will probably learn this. So yeah, good to know. Um, all right, yeah, you can see this. This was actually the every bot design, the one we showed you earlier with the massive dumping thing. There was a single hook for the climbing mechanism and everything. So yeah, guess back to the presentation. All right, yeah, next. Brackets. Okay, so connecting different parts of the robot, right? The easiest way is to use brackets. We can also try and weld them, but usually that's more dangerous and also very difficult. Also, you're not allowed to weld things in the pit, meaning if you fuck up and some issue happens, you're not going to be able to repair in the pit. That's why brackets are usually better. Problem is sometimes brackets can get hit kind of heavy. So what is the purpose? Yeah, is to do that. What materials are they made out of? Steel, sometimes aluminum. Usually we try and use the aluminum ones for the more uh, less important pieces because they're lighter and everything. So the majority of brackets are actually aluminum. But some of the ones for the more key and essential pieces and corners will use steel. There are three of these designs. I don't think you loaded the presentation because there is another one. But there is a right angle design on the top right that looks like that. That's just for the top of the chassis when putting those things together. There's a T-shaped bracket as well. And there's an angle bracket that we use a lot that is not shown in this, bro. I mean, it's there, but I don't think you reloaded the page. Whatever. Um, yeah. Next. Oh yeah, we gotta change the date. All right. Yeah, I think we're good. Next one is Monday, 2:30. Um, if you exit the presentation, yeah, but uh, yeah, that's yeah, Monday 2:30. This week is going to be programming and electrical. It's gonna go back to the same schedule of Monday, Wednesday, Friday, Saturday. Um, yeah, if you guys check, I also put out the what's it called, the attendance form. So please fill that out if you have not. Um, yeah. Oh yeah. Also a reminder: please get your stuff signed. Okay. Everyone who signed in on the roster should have received an email from Mr. Shuckman, or first asking you to get parental consent. You need to go to the website. Get your parents to do the thing. I don't remember exactly what they need to do because I always just ask my parents to do when they did it. But yeah, please do that, or else you can't compete. Yeah, it's essentially what adds you to the official team. So yeah, please do that. In addition, please sign the other stuff in there. We're going to get building soon because we're technically allowed to now. So yeah, you're technically not allowed to do anything, or like not allowed to even enter the classroom unless you like actually sign on those things because safety concerns and all that. So yeah. All right then. Does anyone else have any questions? No? All right, cool. Sounds good then. We'll see everyone on Monday then. Peace.